Chemical properties of group 14 elements. Chemical properties of group 14 elements. Okay. First is oxides. The all the elements of group 14 form oxides of type MO2. Type MO2. Okay. Type MO2. Okay. All the elements of group 14 form oxides. Oxides. Oxides of type MO2, MO2, which are weakly acidic, which are which are weakly which are weakly acidic, which are weakly acidic. Okay. The acidic property decreases with increase in atomic weight from carbon to lead. Okay. 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 The acidic property, the acidic property, the acidic property decreases with increase, decreases with increase, decreases with increase in atomic weight, in atomic weight, atomic weight. Okay. Which are weakly acidic. The acidic property decreases with increase in atomic weight from carbon to carbon to lead. Okay. Carbon to lead. Okay. Carbon dioxide and silicon dioxide are acidic, and gallium dioxide is less acidic, while tin oxide and lead oxide are amphoteric in nature. All these metal dioxide oxides dissolve in bases, giving carbonates, silicates, germanates, stannates, and plumbanates. Okay. CO2 plus NaOH, arrow marker Na2CO3 plus H2O. We will make the balance of this equation. Then number of sodium 1 and number of sodium 2, then 2. Okay. Number of oxygen 2 to 4. No, the number of oxygen 3, 1, 4. Number of carbon 1, 1. And R is equal. Okay. Second point. Silicon dioxide. Silicon dioxide plus NaOH. That is Na2SiO3. Okay. Plus H2O. That is number of silicon 1, 1. Number of sodium 1 but 2. Then 2 number of sodium, oxygen 2 to 4, 3, 1, 4, and hydrogen 1 and 2 hydrogen. Okay. Then next SnO2, tin dioxide plus 2NaOH. Okay. That is Na2SnO3 plus H2O. And fourth PbO2 plus 2NaOH. Okay. Arrow marker for Na2PbO3 plus H2O plus H2O. Okay. The dioxide of tin and lead are also soluble in acids. Okay. Then carbon dioxide and silicon dioxide are acidic. These are carbon dioxide and silicon dioxide are acidic, and germanium is less acidic. and germanium less acidic, and tin dioxide and lead dioxide, okay, are amphoteric nature, are amphoteric, amphoteric, amphoteric in nature, amphoteric in nature, okay, and amphoteric in nature, and all these oxides are dissolved in bases, giving carbonates. All are dissolved in dissolve in bases, in bases, dissolve in bases, okay, dissolve in bases, and the dioxide of tin and lead, and the dioxides of tin and lead, dioxide of tin and lead are also soluble, are also soluble, in in acidic, as example, SnO2, silicon dioxide plus 4HCl, hydrochloric acid, that is silicon tetrachloride, silicon, not silicon, tin stainless tetrachloride, tin tetrachloride, and plus 2S2O. And next is lead dioxide, and plus 4HCl, hydrochloric acid, that is make lead lead chloride, PbCl2 plus Cl2 plus 2H2O, 2H2O. Okay, carbon dioxide is a gas in nature. Carbon dioxide is a gas in nature. Okay, carbon dioxide is a gas in nature. CO2 is a gas, in nature, uh, gas at nature, gas at natural temperature, temperature, natural temperature. It is soluble in water in which unstable carbonic acid. It is soluble. It is soluble. It is soluble in water. It is soluble in water. Water in which unstable carbonic, in which unstable carbonic, carbonic unstable carbonic acid, okay, and H2CO3 is formed carbon dioxide in atmosphere temperature to extent of 0.03% by volume, okay, and solid carbon dioxide has found wide application as a refrigerant under the name dry ice, okay, and solid H2CO3 has H2CO3 is formed. H2CO3 is formed, okay. Carbon dioxide is a gas in natural temperature. It is soluble in water in which unstable carbonic acid, which acid H2CO3 is formed, okay. Carbonic acid H2CO3 is formed, okay. Carbon dioxide occurs in the atmosphere. Carbon dioxide occurs, carbon dioxide occurs, carbon dioxide and carbon dioxide in amphoteric in nature. Okay, solid carbon dioxide has found wide application as a refrigerator. Carbon dioxide occurs in the atmosphere, occurs in the atmosphere, atmosphere, atmosphere to the extent of, to the extent of 0.03% by volume, by volume. Okay, solid carbon dioxide has found wide application. Solid solid carbon dioxide has found wide has found wide found wide application as a application as a refrigerant. Okay, application as a refrigerant under the name refrigerant under the name refrigerant under under the name refrigerant under the name dry ice dry ice dry ice. Carbon dioxide solidifies at carbon dioxide solidifies as solidifies solidifies carbon dioxide solidifies at 79 degree Celsius to carbon dioxide snow to dioxide carbon dioxide carbon dioxide is snow. Okay, carbon dioxide is snow, and it is also used as a fire extinguisher, and 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 it is also used as it it is also used as fire extinguisher fire extinguisher fire extinguisher fire extinguisher. Okay, the three atoms in carbon dioxide molecules are linearly arranged because its dipole moment is zero. The actual structure of carbon dioxide involves unions among the structures. Okay, oxygen, carbon, oxygen, and triple bond, and plus, and 2 to 4 to 6, 1, 2, 3, 4, 5, 6, and a negative, that is first structure, and oxygen, double bond carbon, double bond oxygen, 1, 2, 3, 4, 1, 2, 3, 4. Okay, and this is the second structure. This is second structure, and third is oxygen, triple bond carbon, single bond oxygen, 1, 2, 3, 4, 5, 6, negative, and this is positive. Okay, this is third figure. Okay, carbon dioxide is linear discrete covalent compounds. Okay, CO2 is linear discrete covalent compound. Linear discrete covalent compound. Okay, carbon dioxide is linear discrete covalent compound in nature. Carbon dioxide is linear, discrete, and covalent compound. Okay. In carbon dioxide, carbon forms two sigma bonds and two pi bonds. Okay. Carbon forms in carbon dioxide. In carbon dioxide, carbon forms carbon forms two sigma bonds, two sigma bonds, two sigma bonds and two pi bonds and two sigma bonds and two pi bonds with oxygen with oxygen. The bond length the bond length the bond length carbon oxygen is 1.16 angstrom. 1.16 angstrom indicates the presence of some triple indicates the presence of some triple bond character, some triple bond character. Okay, character. That is why carbon dioxide is a resonance hybrid. That is why carbon dioxide that is why carbon dioxide is a resonance. Carbon dioxide is a resonance hybrid. Carbon dioxide is a resonance hybrid of the above three structure. Okay, above three structure. Okay, and carbon dioxide molecules has overall no dipole moment. Carbon dioxide molecule has overall no dipole moment. Overall no dipole moment. Okay. Carbon dioxide molecule has overall no dipole moment. Since in carbon dioxide molecules only weak van der Waals forces. Carbon dioxide molecules since in carbon dioxide molecules only weak van der Waals van der Waals forces forces of intermolecular intermolecular interaction occurs and show carbon dioxide exists in gaseous form. Okay, due to small size. Okay, 1 minute. Due to small size, carbon forms stable multiple bonds. Carbon forms stable multiple bond, stable multiple multiple stable multiple bond, stable multiple bond. But silicon and other members, but silicon and other members, silicon and other members, but 1 minute. But silicon and other members of this group do not members of this group do not form multiple bond, do not form multiple bond, multiple bond, do not form multiple bond, okay, do not form multiple bond, okay. Silicon dioxide, silica, silicon dioxide, silica, silicon dioxide, silica is a crystalline, solid crystalline solid which occurs in nature in the form of quarters, which occurs in nature which occurs in nature in the form of quarters, okay, in the form of quarters, sand, etc. Quarters, sand, etc. Quarters, sand, etc. It differs from carbon dioxide, which is carbon dioxide, which is a gas, at room temperature, room temperature, okay. Silicon dioxide is a Gantt molecule. Silicon dioxide is a Gantt molecule, okay. Molecule are molecular are macromolecule in which are macromolecule in which all atoms macromolecule in which all atoms are linked by strong bond. Atoms are linked by strong bond, linked by strong bond. In silica, each silicon in silica, okay. In silica, each silicon atom is surrounded tetrahedrally, surrounded tetrahedrally by 4 oxygen atoms, okay. Each oxygen being shared with each oxygen being shared with another tetrahedron, shared with another another tetrahedron, another tetrahedron. Okay. The crystal of silicon dioxide may be treated thus, 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 the crystal of silicon dioxide, thus, the crystal, the crystal of silicon dioxide, thus the crystal of silicon dioxide. Okay, 1 minute. Thus, the crystal of silicon dioxide may be treated, may be treated, may be treated as a Gantt, or micromolecule, or micromolecule, micromolecule, and show silicon dioxide and so silicon dioxide, silica, has a high melting point. High melting point. The structure of silicon dioxide has been, you can show, but you cannot before see the structure of silicon dioxide. Okay. Chemical properties of group 14 element. Listening carefully. Okay. Listening carefully. The chemical properties of group 14 elements. The chemical properties of group 14 elements and their compounds are given below. Oxides. First is oxides. All the elements of group 14 form oxides of type MO2, which are weakly acidic. The acidic property decreases with increase in atomic weight from carbon to lead. Carbon dioxide and silicon dioxide are acidic. Germanium dioxide is less acidic, while tin dioxide and lead dioxide are amphoteric in nature. All these molecular dioxides dissolve in bases, giving carbonates, silicates, germanates, stainless, and plumbates. Okay, stainless and plumbates. Okay, carbon dioxide plus reacted with sodium hydroxide and gave sodium Na2CO3. Okay, Na2CO3 and water and this and different type of okay. And the dioxide of tin and lead are soluble in acids. Carbon dioxide is a gas at normal temperature. Carbon dioxide is a gas at normal temperature. It is soluble in water. It is soluble in water. It is soluble in water. Okay, carbon dioxide is soluble in water. 1 minute. Oh, okay. Carbon dioxide is soluble in. Carbon dioxide is a gas at a natural temperature. It is soluble in water, in which unstable carbonic acid H2CO3 is formed. Carbon dioxide occurs in the atmosphere to the extent of 0.03% by volume, and solid carbon dioxide has found wide application as a refrigerant under the name dry ice. Carbon dioxide solidifies at 79 degrees Celsius temperature, minus 79 degrees Celsius, to carbon dioxide snow. It is also used as a fire extinguisher. The three atoms in carbon dioxide molecules are linearly arranged because its dipole moment is zero. The actual structure of carbon dioxide involves resonance among the structure. Carbon dioxide is linear discrete covalent compound. Carbon dioxide is a linear discrete covalent compound. In carbon dioxide, carbon forms two sigma bonds and two pi bonds with oxygen atom. The bond length carbon oxygen is equals to 1.16 angstrom, indicates the presence of some triple bond character. That is why carbon dioxide is a resonance hybrid of the above three structure. Okay, carbon dioxide molecule has overall no dipole moment, since in carbon dioxide molecule only weak van der Waals process of intermolecular interaction occurs, and show carbon dioxide exists in gaseous form. Due to small size, carbon forms stable multiple bond, but silicon and other members of this group do not form multiple bond. Silicon dioxide is a crystalline solid which occurs in nature in the form of quartz sand. It is and differs from carbon dioxide, which is a gas at room temperature. Silicon dioxide is a giant molecule or macromolecule in which all the atoms are linked by strong bond. In silica, each silicon atom is surrounded by tetrahedrally by four oxygen atoms, each oxygen being shared with another tetrahedron. Thus, the crystal of silicon dioxide may be treated as a giant or micromolecule, and show silicon dioxide, that means silica, has a high melting point. Okay, you can show the structure of silicon dioxide. Okay, structure. Okay, how to create the structure? I 1 minute. Okay, you may relate. This is the silicon, oxygen, silicon, oxygen, silicon. Okay, 1, 2, 3, 4 bond, 1, 2, 3, 4 bond, 1, 2, 3, 4 bond. Sorry, oxygen only two bonds, and silicon is four bond. 1, 2, 3, 4 bond, and oxygen and oxygen and oxygen. And next is silicon at silicon, and that is oxygen, that is silicon 1, 2, 3, 4, and that is oxygen, and that is silicon. Okay, silicon. Oh, 1, 2, 3, 4. Okay, and next oxygen, oxygen added by single bonding, and that is silicon, and that is 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, this is the structure of silica. This is the structure of silica. Structure of silica. Structure of silica. SiO2, silicon dioxide. Okay. The element of group 14 also form monoxides of type of MO. Okay. Okay. Then the elements of group 14 also forms the elements of group 14 also form monoxides of the type MO. Okay, carbon monoxide is neutral. Carbon monoxide is neutral. Is a neutral. Carbon monoxide is neutral. Silicon dioxide is little known, and carbon monoxide, silicon monoxide is little known. Is a little known, little known. Okay, little known. While stainless monoxide, while stainless monoxide and lead monoxide are mainly basic, are mainly are mainly are mainly basic, mainly basic mainly basic, with some amphoteric character, with with some amphoteric amphoteric with some amphoteric characteristics characteristics characteristics. Okay, silicon monoxide, SiO, and germanium monoxide, GU, are unstable, unstable, while while other oxides are quite stable, are quite stable, quite stable. Okay. The element of group 14 is also found monoxide of the type of MO. Carbon monoxide is neutral. Silicon monoxide is little known, while stainless monoxide and lead monoxide are mainly basic with some amphoteric characteristics, and silicon monoxide and germanium monoxide are unstable, while other oxides are quite stable. Okay. Next, highlights. Second point, highlights. Okay. The element of group 14 also form monoxide of the type of MO. Carbon monoxide or CO is neutral. Silicon monoxide is little known, while stainless monoxide and lead monoxide are mainly basic with some amphoteric characteristics. Silicon monoxide and germanium monoxide are unstable, while other oxides are quite stable. Okay. Next is highlights. Highlights. The element of group 14 form tetrahalides of the type of MX4. Okay. MX4. Okay. Where M equal to the elements of group 14 form tetrahalides of the type of MX4, where M equal to carbon, silicon, germanium, tin, and lead. Okay, and X equal to halogens, fluorine, chlorine, bromine, iodine. Okay, and the tetrahalides are covalent in nature. Tetrahalides are covalent in nature. SnF4, however, possesses ionic character, and stainless fluoride is stainless fluoride, however, possesses ionic character. The tetrahalides are tetrahedral in structure due to presence of sp3 hybridization, and hybridization is sp3 hybridizations. Okay. The chlorides are all volatile liquids. Okay. The chlorides are all The chlorides are all volatile, volatile, volatile volatile liquids. Okay, all halides, all halides, all halides except carbon tetrachloride. Carbon tetrachloride undergoes hydrolysis. Undergoes hydrolysis. Undergo hydrolysis. Okay. Then the reaction MX4 plus 2H2O, that is MO2 plus 4HX. Okay. As an example, silicon tetrachloride plus 3H2O, that is H2SiO3, silicic acid. This is silicic acid plus 4HCl hydrochloric acid. Okay, and SiCl4 silicon tetrachloride is reacted with water of 4 molecules, then is make SiOH whole 4 plus 4HCl hydrogen chloride acid, and SiF4 silicon tetrafluoride is reacted with 4 molecules of water, that is make SiOH4 plus HF. This is orthosilicic acid. This is orthosilicic acid. Okay, this is this is silicic acid. This is orthosilicic acid. Orthosilicic acid. Okay, acid, orthosilicic acid, and stainless tetrachloride is reacted with 4 molecules of hydrogen water, that is make orthostanic acid, SNOH4, orthostanic acid plus 4HCl. Okay, hydrogen chloride. Okay, and 3SiF4 plus 4H2O, that is make SNOH4 orthostanic acid plus 2H2SiF6 hydrofluoronosilic acid. Okay, hydrofluorosilicic acid, and 3 molecules of silicon tetrafluoride reacted with 2 molecules of hydrogen water, that make silicon dioxide, SiO2, silicon dioxide plus 2H2SiF6, that is hydrofluorosilicic acid. Okay, that is hydrofluorosilicic acid. Silicic acid. Okay, and the carbon chlorine bond, and the carbon chlorine bond, chlorine bond is weaker than carbon chlorine bond is weaker weaker than silicon chlorine bond. Silicon chlorine bond SiCl4 is hydrolyzed but CCl4 is not hydrolyzed. Si silicon tetrachloride is hydrolyzed 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 but CCl4 carbon tetrachloride is not hydrolyzed okay. This is due to presence of d orbital in the outermost configuration of silicon and absence of d orbital in carbon. The resistance of carbon tetrahalide to hydrolysis is explained by the covalently saturated character of carbon, but silicon is coordinately unsaturated in tetrahalides, maximum covalency 6, which therefore radially undergo hydrolysis process. Okay, you can show as an example of hydrolysis process. Okay, then this is silicon tetrachloride, that is silicon, chlorine, chlorine, and chlorine. That is reacted with two molecules of water and make silicon and chlorine. That is chlorine and that is chlorine and oxygen, hydrogen and hydrogen, that is hydrogen chlorine bond, that make hydrogen chlorine bond and that is make chlorine, that is oxygen, hydrogen, okay, that is hydrogen chlorine bond, and that make silicon, chlorine, H unstable, chlorine and OH, that unstable and reacted with two molecules of hydrogen chloride and that make and the presence of two molecules of water and that make silicon hydroxide and hydroxide. Okay, that is stable plus 2HCl. Okay, then germanium tetrachloride and germanium tetrabromide are more readily hydrolyzed than the silicon halide. Okay, germanium tetrachloride and germanium tetrabromide are more readily hydrolyzed than the silicon halides. Okay, carbon tetrachloride is saturated molecules, hence it cannot form coordinate bond with water because it does not contain vacant d orbitals. Hence, carbon tetrachloride is not hydrolyzed by water. Okay, the other elements halide get hydrolyzed by water because they form coordinate bond with water, max covalency 6, due to presence of vacant d orbitals in their outermost electronic configuration. Complex anion of the type MX6 2 negative ion is found by the tetrahalides except carbon tetrahalides. Okay, fluosilicate SiF6 2 negative, and fluostenate SiF6 2 negative, and chlorostenate SnCl6 2 negative, etc., are well known due to the availability of d orbital, thereby their coordination number increases to 6. sp3d3 hybridization occurs in mx6-2 type complex ion, and structure is octahedral. The halides of group 14 elements act as strong Lewis acid because they accept lone pair of electrons in their vacant d orbitals, except carbon halides. Okay. Next point. Next point. Acid-base nature of compound. Acid-base. Acid-base. Acid-base nature. Acid-base nature of compounds. Acid-base nature of compounds. Acid-base nature of compounds. All the elements form oxide of the type of MO2, and these are acidic oxides, giving salt upon dissolving in alkaline. Okay, alkalis. Okay, all the elements form oxides of the type of MO2, and these are acidic. These are acidic oxides, giving salts upon dissolving in alkaline, and giving salt, and giving salt upon dissolving in alkalis. Upon dissolving in alkalis. Okay, as example, carbon dioxide plus 2NaOH, sodium hydroxide, that make a sodium carbonate, Na2CO3, sodium carbonate plus H2O, water. Okay, germanium oxide and stainless oxide and lead oxide, amphoteric. Germanium oxide, GeO2, stainless oxide, and lead oxide, PbO2, lead oxide, are amphoteric. And carbon monoxide is natural, is a neutral. Carbon monoxide is neutral. Okay, carbon monoxide is neutral. Carbon monoxide is neutral, while stainless monoxide and lead monoxide are amphoteric. Okay, and SnOH whole twice, lead OH whole twice, and hydroxide of stainless lead are also amphoteric, and SnOH whole twice, PbOH whole twice, and SnOH whole 4, and PbOH whole 4 are also amphoteric. Okay, and H2CO3 and H4SiO4 are weak acid. Weak acid, and carbonate ion is hydrolyzed, and sodium is basic. Okay, then CO3 2 negative plus H2O, that is HCO3 negative plus OH negative. Okay, and reaction with alkalis. Next, reaction with alkalis. Okay, reaction with alkalis. 1 minute. Reaction with alkalis. Next point, reaction, reaction with alkalis. Reaction with alkalis. Reaction with alkalis. Okay, reaction with alkalis. Except carbon, the other elements dissolve in sodium hydroxide and liberate hydrogen gas. Okay, except carbon, except carbon, except carbon, the other elements dissolve, the other elements dissolve, 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 except carbon, the other element dissolve in sodium hydroxide, sodium hydroxide, in sodium hydroxide, in sodium hydroxide, and liberate hydrogen gas, and liberate and liberate hydrogen gas, liberate hydrogen gas, hydrogen gas. Okay, as example, silicon plus 2 sodium hydroxide NaOH and plus water H2O, that make Na2SiO3 plus hydrogen gas, hydrogen gas, and stainless ashen plus 2NaOH, that is cold sodium hydroxide cold, that make Na2SnO2 plus H2 hydrogen gas. Fifth point, acidic, acids. Okay, acids. All the elements of group 14 form acids of type of H2MO3. Okay, all the elements of group 14 forms acids of type H2MO3. H2MO3 where M equal to carbon, silicon, germanium, stainless, and lead. Okay, and lead. Okay, 1 minute. That is tin and lead. Okay, carbon, silicon, germanium, tin and lead. Okay, and the sodium salt of these acids are stable. The sodium salt of these acids are stable. Carbonic acid H2CO3, silicic acid H2SiO3, metastannic acid H2SnO3, and metaplumbric acid H2PbO3. Okay, the sodium salts of these acids are stable. The sodium salts of these acids are stable. Acids are stable, and example, carbonic acid, H2CO3, that is example. Okay, carbonic acid, okay, H2CO3, and H2SiO3, that is known as silicic acid, and H2SiO3, that is silicic acid, and H2SnO3, O3, that is metastanic acid. Metastanic acid, and H2PbO3, that is metapolymbic acid. Metapolymbic acid. Okay. And next point, 6 point, hydrides. 6 points, hydrides. 6 points, hydrides. Okay. Hydrides. Next point, hydrides. Okay. What is hydrides? The all the elements of group 14 forms covalent and gaseous hydrides of the type of MH4. Okay. All the elements of group 14s, all the elements of group 14 all the elements of group 14 form covalent and gaseous hydrides. Form covalent and gaseous hydrides. Okay. Gaseous hydrides of the type MH4. MH4, carbon forms a large number of hydrides which are called hydrocarbons. Carbon forms a large number of hydrides that is known as hydrides which are called hydrocarbons. Which are called hydrocarbons. Which are called hydrocarbons. Okay. And hydrocarbons are of two types, aliphatic and aromatic. And hydrocarbons are of two types. Hydrocarbon are of two types, aliphatic and aromatic. Aliphatic and aromatic. Aliphatic and aromatic. The aliphatic compounds are of three types. Okay. The aliphatic compounds are of two types or three types. Aliphatic compounds are three types. First is alkanes, paraffins. First is alkanes, that is known as paraffin. Paraffins, CnH2n plus 2. Second is alkenes. This is known as olefins. That is known as olefins. Okay. Olefins, and formula is CnH2n. Okay. And third is alkynes. Alkynes, that is known as acetylenes. Acetylene. Okay. Acetylenes, that is known as acetylene. CnH2n minus 2. This is the formula. CnH2n is plus 2 is the formula of alkanes, that is known as paraffins, and CnH2n is the formula of alkenes, that is known as olefins, and CnH2n minus 2 is the formula of alkynes and is known as acetylenes. Okay. Alkanes are saturated hydrocarbons. Okay, alkanes are saturated hydrocarbons. Alkanes are saturated hydrocarbons. Alkanes, that means paraffins. Alkanes, alkanes, alkanes are saturated hydrocarbon. Are saturated hydrocarbons. Saturated hydrocarbons. Alkanes are saturated hydrocarbons, whereas alkenes and alkynes are unsaturated. And where is alkenes, alkenes, alkenes and alkynes are unsaturated hydrocarbons, unsaturated hydrocarbons. Okay, hydrides of carbon are known as hydrocarbons, which are the basis of organic chemistry. Okay, hydrides of carbon are known as hydrocarbons, which are the basis of organic chemistry. The stability of MH4 types hydride decreases with increase in atomic weight. Okay, the stability of MH4, stability, stability decreases with increase in atomic weight, with increase in atomic weight. Okay, the hydrides are known as methane. As methane, silane, and styrene. Okay, the hydrides are known as methane. Okay, methane, CH4, methane, and SiH4 is a silane, silane, and SNH4 styrene, and GeH4 is germane. Okay, and PbH4 is plumbane. So later PbH4 is least stable and has a doubtful existence, and plumbane PbH4 is least stable, and has a doubtful existence, doubtful existence, doubtful existence. The thermal stability of hydride decreases as we move down the group. Okay, the thermal stability of the hydride, the thermal stability of the hydride, the thermal stability of the hydride decreases as we move down. Okay, and the molecule, and that is a thermal dissociation temperature. Thermal dissociation temperature in degree Celsius. That is molecule methane. Thermal dissociation temperature 800 degrees Celsius. And SiH4, that is known as silane. silane. The thermal dissociation temperature is 450 degrees Celsius, and GeH for German, that is 285, and SNH4, SNH4, silane, SNH4, that is silicon, and stannane, that is stannane, and dissolving dissociation temperature is 150 degrees Celsius, and PbH4, that is known as plumbane, and dissociation temperature is 0 degree Celsius. Okay? Then silicon forms a number of hydrides of type SnH2n plus 2, which are analogous to the hydrocarbons saturated. The simplest member, monosilane silicomethane SiH4, is a representative of the series. It is prepared as Mg2Si plus 4HCl, that is 2MgCl2 magnesium chloride plus SiH4, okay, and it reacts with bases and evolve hydrogen gas. It reacts with bases, it reacts with bases, and evolves hydrogen gas. As example, SiH4, silane reacted with 2 molecules of sodium hydroxide, and on the presence of water, that is make Na2SiO3 plus 4 hydrogen gas. It is a strong reducing agent, reducing silver iodine to metallic silver. Okay? It is a strong reducing agent, reducing silver first to metallic silver, For example, 4AgNO3, silver nitrate plus SiH4, that is silicon plus 4Ag, silver plus nitric acid, 4HNO3 nitric acid, 4HNO3 nitric acid. The silanes are as follows. 1 minute. The silanes are as follows. N equal to 1 to 6 in SiNH2n plus 2. Okay, that is SiH4, Si2H6, Si3H8, Si4H10, and Si5H12, and Si6H14. The name is monosilane. That is monosilane, disilane, and this is trisilane, and this is tetrasilane. This is tetrasilane. This is pentasilane, and this is hexasilane. That is hexasilane. Okay. Higher silence also react with alkalis and evolve hydrogen gas. Okay. Okay. And higher silence, higher, higher silence, higher silence also react with alkalis, also react with alkalis, react with alkalis and evolve hydrogen gas and evolve hydrogen gas, evolve hydrogen gas. As example, Si2H6 plus 4 potassium hydroxide plus 2H2 water, that is make 2K2SiO3 plus 7H2. Okay. The number of hydrides of tin, and lead are limited due to less catenation ability. The hydrides formation decreases as we move down the group. Okay, the hydrides formations, the hydrides, the hydride formation decreases. Hydrogen formation decreases as we move down the group. As we move down the group. Okay, move down the group. Okay, and germanium also forms GeH4, Ge2S6 and Ge3H8 etc. Okay, these are prepared by heating germanium oxide with LiLH4. The hydrides of germanium are called germanes. Okay, the hydrides of germanium are called germanes. Are called germanes. Are called germanes, which are resistant which are resistant to hydrolysis. Okay, hydrolysis. Okay, tin forms SN4 hydride. Tin forms SN4 hydrides. Okay, tin forms SN hydrides stannate SnH4, which is obtained by the action of hydrochloric acid on SnMg alloy along with hydrogen. Lead hydride PbH4 plumbrine is an extremely unstable gas. It is produced by electrolytic reduction at a small lead cathode under high current. Okay. Next point, complex formation. Next point, 7 point, complex formation. Next point, complex formation. What is complex formation? The complex formation or tendency of an element is favored by three factors which are given below. First is high charge. Second is small size, and third is availability of vacant empty d orbitals. Availability of vacant empty d orbitals. Okay, empty d orbitals except carbon in the tetra-covalent compounds of other elements. There is an availability of empty d orbitals. Okay, except carbon in the tetra-covalent compounds in the tetra-covalent compounds covalent compounds of other elements of other elements. There is an availability. There is an availability of impurity d orbitals. Okay, these elements therefore can form complexes and thereby increase their coordination number from 4 to 6. Okay, these elements therefore these elements therefore these elements can form complexes can form complexes 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 and thereby increase their coordination number from 4 to 6. Okay, as an example, if we will be talking about example of a complexes compound, you can show also this compounds SiF4 reacts with 2F negative ions and form complex as SiF4 plus 2F, that is SiF6, that is 2 negative, and similar is in the case with similar is the case with SnCl4, that is SnCl4 and plus 2Cl negative, that is form SnCl6 minus 2 negative. In these cases, 4 covalent and 2 coordinate bonds are formed as a result of sp3d D3 hybridization, which gives an octahedral structures. Okay, in these cases, four covalent and 2 coordinate 4 covalent and 2 coordinate bonds are formed as a result of sp3d3 hybridizations, which gives an octahedral structures. This can be explained as follow: silicon 40, that is known as I1s2, 2s2, 2p6, and 3s2, 3p2. Electronic configuration of silicon atom ground state. Okay, electronic configuration silicon atom ground state. Okay, that is 3s and that is 3p and 3d, that is 3d 1 2 3 4 5. Okay, and silicon atom excited state, silicon atom excited state, excited state, excited state, that is excited state, okay? Silicon atom, excited state, and sp3 hybridization, sp3 hybridization, sp3 hybridization in SiF4 molecule, that is sp3 hybridization, sp3 hybridization, and this is 1 2 3 4 1 2 3 4 5, okay, the orbitals, and sp3d2 hybridization, hybridization in SiF6 -2 complexation, that is one two, and that is 1 2 3 4, that is okay, that is sp3 hybridization, okay, sp3 hybridization, that is fluorine negative, that is sp3 hybridization, sp3 hybridization, sp3d2 hybridization, sp3d2 hybridization, as a structure, octahedral structure as sp6, sf6 2 negative ions is you can show this -2 negative, that is silicon, and fluorine, okay, fluorine, and okay, and that is fluorine, okay. This is the structure, octahedral structure of sf6 2 negative ions, okay, and this is chemical properties of group 14 elements is in there, and next is gradation in properties, okay, gradation in properties of group 14 elements, okay. Highlights the element of group 14